Hello friends, now we are going to talk about the fourth module, that is nothing but the metal semiconductor devices. Okay, now actually in this module, what we are going to understand that when we are trying to form the contacts or trying to contact the two materials together, or join the two materials together and form a particular transistor. So what are the properties happening at the uh, boundary between the two different material, that is when we are trying to connect the metal and the semiconductor together, then what are the difficulties we will be facing and how to overcome that difficulties. Okay, that we are going to understand through this whole module. Okay, when we are trying to join the metal and the semiconductor, obviously there is the problem of the barrier, and how that barrier is getting formed. Let's try to understand here. So the formation of the barrier. So when we are trying to form the contact between the metal with the semiconductor, the barrier is formed at the interface. Okay, so this barrier is actually responsible for the controlling the current conduction as well as its capacitive behavior. Okay, so let's try to understand that the basic energy diagrams leading to the formation of the barriers. Okay, here I have drawn the four different kind of the energy diagrams corresponding to the metal and the semiconductor one. Okay, so the ideal condition which we are going to understand here is the ideal condition. Okay, now let's consider the ideal case without the surface states and the other anomalies. Okay, so the first figure. Okay, so the separated system, that the metal system is on the left hand side and the semiconductor system on the right hand side. So what it shows, actually the electronic energy relations of high work function metal and the n-type semiconductor, which are actually not in contact, and they are considered to be the separate systems. If they are just try two systems are allowed to communicate with each other. Okay, if we just bring them close together, so what is going to happen, what type of the communications they do with each other. So let's try to have the understand how the example is something like wire connection between them. If we just try to make them, then the charge will try to flow from the one system to the other, that is from the semiconductor to the metal, the charges will flow, and the thermal equilibrium is established and considered as a single system, right? So the Fermi levels on the both the sides will line up. So whenever we are just trying to connect the two metals to metal and the semiconductor together, then obviously their Fermi level just coincide with each other, or they should line up in the at the same state. Okay, so relative to the Fermi level in the metal, okay, if Fermi level in the metal, the Fermi level in the semiconductor is lowered by an amount which is equal to the difference between the two work functions. So the how much is work function for this, and the how much is work function for the semiconductor. So the difference is something we call it as a relative Fermi energy in the metal. Okay, and that is given by the difference between the two work functions. So now work function is nothing but the energy difference between the vacuum level. Okay, so this is nothing but this is the vacuum level, and this is what we can say the Fermi energy level. So the difference between these two is nothing but the work function, phi m. Okay, it is represented with the values of phi. So phi m is the work function, and m stands for the metal. Okay. So this quantity will be denoted by the phi m for the metal, and which is equal to the q phi n plus q chi. Okay, q chi for the semiconductor, as we can have, that is q chi is the electron affinity measured from the bottom of the semiconductor, sorry, bottom of the conduction band EC to the vacuum level. So this is the electron affinity in the semiconductor. And q phi n, okay, q phi n is nothing but the energy difference between the EC, that is the conduction band energy, and the Fermi level. Okay, so the potential difference between these two, okay, so the potential difference between these two is nothing but the between the two work functions, that is phi m. Okay, so the here I am just trying to write down, that is nothing but the q or the phi m minus the chi plus phi n is called as the contact potential. So this is called as the contact potential. Okay, so as if we just try to reduce this gap distance delta, or try to reduce this delta between the metal and the semiconductor material, the electric field in the band gap get increases, and increasing negative charge is built up at the metal surface, because when we are just trying to reduce this distance, obviously the potential difference which is applied across it will result as to the increase in its electric field, because electric field is the potential developed upon the distance of the separation. Okay, so what will happen? The negative charge will be developed on the metal surface. So an equal and opposite charge, that is the positive charge, must exist in the semiconductor depletion region. So the that much charge will be present in the depletion region of the semiconductor. So the potential variation within the depletion layer is similar to the one side of the p-n junction, right? So this is acting as something like one side of the p-n junction. So here the delta is small enough to be comparable to an interatomic distances, and the gap becomes transparent to the electron. So this becomes a very small one, and obviously this gap becomes transparent for the electrons, and so electrons can easily just jump from the one material to the other one, or just its Fermi level gets aligned. So we can obtain the limiting case which can be shown over here as well, right? So it is clear that the limiting value of the barrier height, that is this is nothing but the barrier height. Okay, so that is represented with q phi b n o, which is given by q times phi m minus chi. Okay, so the barrier height is simply the difference between the metal work function and the electron affinity of the semiconductor. So conversely, on the other hand, for an ideal contact between the metal and a p type of the semiconductor, if we just try to reverse the polarity, then what we can have is barrier height is given by the q phi b po is equal to Eg minus q plus phi m minus chi. So Eg is something around the other side we are just trying to understand, because the Fermi level which will be lying near to the valence band edge. So for any semiconductor and the metal combination, okay, semiconductor and metal combination here, whichever we have shown it, is the sum of the barrier heights of the n type and the p type. Okay, n type and the p type substrate is expected to be equal to the band gap. Okay, so in fact, in real practices, the simple expressions for the barrier heights which is given by this equation, okay, this as well, okay, are never realized experimentally, but they do exist. So the electron affinities of the semiconductor and the work functions of the metal, okay, electron affinities and the work functions of the metal have been established. So for the metals, q phi m, okay, q phi m is the order of the 2 to 6 electron volt. Okay, 6 electron hole. So values of the q phi m are generally very sensitive to the surface contamination. Okay, so the do remember that work function can be reduced or the increased by the surface contamination. So the most reliable values of the clean surfaces can be seen over here in this figure, which are not shown here, but for the various different materials it is shown in the our reference book. Okay, and so the main deviations of the experimental barrier heights from the ideal conditions are something like the unavoidable interface layers, that is, a delta becomes is never zero, as we do remember it here. Okay, if this delta goes on decreasing, but it never goes to the zero, so do remember it. Okay, and the presence of the interface states. Okay, and due to the presence of the interface states, and it is also not possible to have. And so the barrier height can be modified due to the what we can say is nothing but the image force lowering. Okay, image force lowering, do remember this thing. So how the barrier height can be modified. Okay, image force lowering. So these effects will be discussed in the following sessions.